All right, let's get started with the next session. So we'll have two talks in this session, 45 minutes each. The first speaker is Debaprasad Maity from IIT Guwahati, and he'll be talking about magnetogenesis from inflationary perturbation and axion and its GW signatures.
Okay, so thank you, Rajiv. And also thanks to the organizer for inviting me to come here. And this is my second time, by the way. If you look at the title, so the topic partly is basically it has three parts. One is the magnetogenesis. Another one is how action is related to magnetogenesis that I'll be talking about, and then how from there I can produce some interesting features about the gravitational wave. Okay, so before I start, let me just give you the pictures, some of the beautiful pictures of our campus. Yes. So just to attract you people, if you're interested, you can definitely write to me and come here, visit us. It's very nice. I think one of the most beautiful campus in India, I would say, because everything is there actually. Yes, drone. Yes, it is mostly from here. So lakes, rivers, hills, everything is there except, of course, the ocean. Otherwise, everything is there. Okay, so the question that we will be asking here in this talk is how does our universe become magnetized at all scale? Okay, I will be particularly talking about what would be the strength of the magnetic field, but how can I generate in a pretty much generic way the magnetic field at all scales in our large scale universe. Okay, so the present universe is definitely an outcome of a single experiment that had happened 13 billion years back. We cannot perform anymore. Only thing that we have to do is to look at the various relics at the present moment and try to understand those relics. What are the origin, what are the physics behind this, and all that. Okay, and the primary relic that we see today is one of the most discussed ones, of course, the CMB. And you have already heard several talks on this particular topic, how that CMB can help us understand how universe evolves, what are the fundamental physics that controls the universe and everything. And then another one is, of course, like light elements that we see today, which is the outcome of the BBN that happened around 100 seconds after the Big Bang. Similarly, you can have dark matter, which we, of course, don't know. Dark energy can be a good relic of the universe. And then, of course, the gravitational wave that we have been discussing throughout this conference. Okay, most of these things we have discussed in this conference in some way or the other, but very less discussed is the one that I'll be talking about, which is, of course, another relic of the early universe cosmology, is the large-scale magnetic field. Okay, so magnetic field exists at across all sorts of scale. Okay, and we know how this magnetic field plays very important role in evolving or in particularly formation of the stars, formation of the intergalactics, the galaxy stars, everything. So everywhere, whatever you go, at various scales, you will find the presence of magnetic field. Okay? Most galaxies, including our Milky Way, you know that it contains a large magnetic field of significant strength with a very large coherence length scale. Like the strength of the magnetic field of the order of microgauss, and the length scale, meaning that how long that value of this magnetic field can sustain, is of the order of 1 to 10 kiloparsec, which is typical of the size of the galaxies. Similarly, if you go a little larger length scale, like galaxy clusters, then also the similar amount, similar magnitude of magnetic field strength that you can observe. And which is again, the length scale is of the order of 10 to 100 kiloparsec. Now you can go further, like at the around megaparsec scale, and which is the perfect place is the CMB, where you can talk about megaparsec scale size. And this megaparsec scale, at this scale also, of course, the CMB, they have not seen the magnetic field, but at least they can put a limit that what should be the magnetic field strength at that megaparsec scale by looking at the correlation, various correlation in the CMB. So from this various observations and various presence of the magnetic field, what we can see that as we go deeper and deeper, because if you look at larger and larger length scale, essentially you are going backward in time in some sense. So in that sense, as you go deeper and deeper, early universe, it seems that magnetic fields everywhere present. So it's widespread. So in some sense, it is like hinting towards us that maybe the origin of this magnetic field is not only the astrophysical, maybe some cosmological origin. Okay, so whatever I just said can be summarized in this simple plot here. This is the length scale, and this is the strength of the magnetic field. And this white region is the one that I have just spoken, the galaxy and galaxy cluster strength of the magnetic field. And remaining ones is related to somehow the upper bound that is set by various observations like BVN and then CMB. And then if you increase the strength of the magnetic field further, then of course there are various other effects which will basically tell you that it is not there at that scale. Okay, so but in this plot, the most important thing that is coming up apart from this is the one that is this blue mesh. Okay, what is this telling you? It is essentially telling you that magnetic field should exist in some sense, because it is telling you that the universe contains at large length scale, universe contains some amount of magnetic field because it sets the lower bound. What is this observation all about? This is essentially the observation of TeV scale of gamma ray observation from the source of blazar. Okay, and this blazar, from the blazar source, what is happening? The TeV scale photon is coming towards us. It's a Fermi observation. So, and the distance of this blazar is around this gigaparsec scale. And when these photons are coming, then what we expect that since the energy of this photon is extremely high, then in between this path, it can interact with the background light of lower energy and produce electron-positron pair. And that electron-positron pair, as it further progresses towards us, it can hit the background CMB photon. It can transfer energy to the CMB photon, and CMB photon can gain amount of energy and become a GeV photon as it comes to us. So that means if I look at this distant blazar from the theoretical perspective, meaning whatever processes that we know up in the standard model, we would expect not only this TeV photon, but surrounding by this, there is a halo of GeV photon. So that is what typically we expect in the standard model. And this is what the spectrum is. If this dotted line, this dotted line, that is what the expected spectrum that we should see from the blazar. But what we see is that these are the data points. Of course, we are not talking about this because this is just a very high energy photon that cannot be explained right now. But at least we see that there are significant, all the photons that we see is around in this energy. And this is the gamma ray range, and these are the detector sensitivity. And this is what the expected gamma ray distribution, GeV photon that you should expect from this blazar. Within this detector sensitivity, this is the expected basically GeV photon, but they have not seen it basically. So So non-observation of this expected GeV photon, which is the halo surrounded by this GeV photons, is essentially explained by this this group. Is that there must be some intergalactic, very long scale. It is not the random magnetic field. It should be intergalactic magnetic field, which is a very large coherent scale, such that what is happening, this electron, because the charged particle interacting the magnetic field, will deviate from the line of sight. So, so gamma ray photon that you are expecting would be extremely less poor. So that is what the typical observation. And the explanation of this particular non-observation of this gamma ray photon is saying that you must have intergalactic magnetic field of strength of this order, and it should be it essentially setting this lower limit. So yes. Some of the blazars you are talking about. Okay, yes.
See some, so you're saying that we usually see this double hum structure for the spectral energy distribution.
Yes, yes.
And what you're showing, that's the inverse Compton photons and the, yes.
Yes, this is the inverse Compton, yes.
Correct. So what you're saying is that these other GeV photon which are expected are missing.
Not seen, yes.
Because of the spectral characteristics are very different for the inverse Compton versus the direct one, which you come from the pair production and things like that.
Yes.
That's the statement, right?
No, the statement is this GeV photon is, we should expect, so apart from this TB photon, we should expect a kind of halo kind of GeV photon, which should come because of this inverse Compton effect.
Yeah, but we do find, double hum structure for the spectral energy distribution. So
but this is the observation.
Correct.
But this has not been observed. That is what the point is.
Okay. Oh, the scales are slightly lower.
Yeah. Okay. So whatever. So this is the expected spectrum. These dotted lines.
Yeah.
And these are the data points.
So it's slightly Okay.
Yeah. So
it's a logarithmic thing.
Yeah. So this is there is no data point in this region, which is the gamma ray spectrum.
Okay.
This GeV spectrum.
And this is sort of independent of the distance to the blazer. That's
no. It is of course depending on because it has to be like very because typical length scale at which this TeV scale photon will convert into electron positron is around 100 megaparsec.
Yeah, yes. Sure. But
so if it is within that, then of course you will only see the.
There are not many such that. Yes. So you have to go. Yeah.
Yes,
okay.
Yes.
Thank you. That's very clear.
Yes, there are. No, which double hum? No. Okay, so what we see is this data point. Yeah. And what is expected.
Yeah, but at the laser itself,
yes.
There are these low energy photons apart from the gamma ray photons.
Yes, from here, of course, there are.
Those will also give you that. The high energy.
Yeah, you are saying if there is a conversion of those photons into through some processes, that can be expected. So what I'm saying, if you don't have this kind of processes from the blazar, this is a spectrum, pure blazar. If there is no other processes, this is the blazar spectrum. This is typically a model dependent what kind of model you are making of this blazar. But this dashed line is the pure blazar spectrum, and then if this process is happening within this, then the spectrum will get changed to this dotted line, and then because these are the physical process that is happening, but we don't see this. Okay, so that is the good point. So basically, non-observation always has this point, because you can always ask a different type of thing. So there are different explanations. People have tried to explain this kind of non-observation by some plasma instability, when this electron positron is coming and then it hits with the plasma, and then it can lose some amount of energy into the plasma, then inverse Compton effect will not be very efficient. But there is a debate. Yes, there is other processes by which people have also tried to explain these non-observations, but there is a debate. It is not settled, but because plasma instability time scale has to be very small compared to the inverse Compton time scale. So there are some debates, which is not completely settled, but I think this is currently the most popular explanation of this particular non-observation. Okay. Okay, so so basically what it tells you, these are upper bound, these are lower bound, that means the universe should be filled with magnetic field at all scales. So that is what I'm taking as a face value. Okay, so what are the origin that by which we can produce this magnetic field? The popular one is of course the galactic dynamo mechanism. So this is essentially a nonlinear process, which essentially what it does, it transfers the kinetic energy of the plasma into the magnetic field, which is a kind of causal process. And growth, this if dynamo starts to act, then it growth, if there is a sufficient environment of this plasma, depending on the modeling of the plasma, this growth continues until it reaches a saturation point, which is about 10 to minus 6 Gauss or 10 to 9 Gauss around. But one of the main point of this dynamo process is that how do you produce such a long coherent scale magnetic field? That is point number one. And point number two is that in order to obtain, in order to activate this dynamo process, you need to have seed field. So that is the typical, you need to have a seed field such that that seed field is going to get enhanced by this dynamo process. Of course, there is popular mechanism by which you can produce the seed field, which is called Biermann battery. But it turns out that the amount of seed field that it generates, this Biermann battery, is extremely small, which cannot be of the order 10 to minus 2 Gauss. So this is one of the problems that I will be keep coming in our subsequent explanation. Okay, so the second mechanism is of course the primordial one. And the one that I will be talking about today is the inflationary magnetogenesis, because inflationary magnetogenesis gives you a very easy explanation, because okay, so I'll come to that point. And then another one is also very popular, which people have been working on, is the phase transition, the electroweak scale. And then the one that has not been discussed at all, mostly, I was very, I mean, there is no paper, at least 1-2 papers, except 1-2 papers, I have not found much of a discussion of the primordial magnetogenesis from the inhomogeneous. So that is what today I'll be talking about. These are the two things that I'll be talking about. Okay, so before I go on, let me just explain a bit how all these scales are coming into the picture. So you have already seen this picture before. Rajiv also mentioned this, and in the earlier talks also you have seen this kind of. So basically what it tells you that this is the inverse 1/h scale, inverse Hubble scale, 1/h. So this telling you that during the inflation, this is going down, the scale is going down, horizon scale is going down. And then after that, your inflation ends, and then there is subsequent whatever evolution that you can think of based on your model. And the physical scale is whatever is happening in this. That means any causal phenomena, any phenomena that happens in this period, you would expect that those effects will be seen at all scales, because those are the scale that you see today. Whether, on the other hand, if you assume that some phenomena, the phase transition that I was talking about, happens not during this period, it happens during this period. So that is why what happens, whatever phenomena that has, which can produce a magnetic field, always limited by a scale, because it cannot produce these scales. Because these are the causal phenomena, anything that you can produce, which should be, maximum scale should be around this size, if something happened during this period. Of course, there are nonlinear processes or inverse cascade. Those are the things that people do talk about, where magnetic field can be converted from low scale to high scale, but that is right now, let us not worry about this. So this is how all this happens. That means any process that happens during this period, I would expect that will create the magnetic field at all scales. So that is why this particular inflationary magnetogenesis is very convenient to generate magnetic field at all scales. Okay, what is the goal now? Goal is that produce magnetic field at all scales, and around this scale, around this scale, I should expect the magnetic field should be of this strength. So I'm just writing it this two separate. I want to make it as a two different problem here. One is how to generate magnetic field at all scales, even though it is very weak, but how to generate that. And then another one, how to make them sufficiently strength. So these are the two problems. I'm trying to make it a separate problem so that it will be easier for me to discuss. So, and particularly if you are talking about this particular point that produce magnetic field at scale, inflationary magnetism is the best. Because there is no other mechanism which can do this. Because you can see, look at this picture, then you can easily understand. Okay, the main point then would be, even though I can produce some magnetic field at all scale, but how can you generate a magnetic field of that particular strength is required to solve that seed field problem that I was mentioning. Okay, so there are widely popular models are there. First example that we'll be talking about is the popular one, which is what you do, you couple the gauge field with some scalar field, which is called typically the conventional Ratra. It's a Ratra model. Ratra first proposed this idea. And then you take this usual FLRW metric background, inflationary background, and this this function, this essentially you don't assume typically what is the dynamics of phi. Of course, you can assume the dynamics of phi and then do the analysis. But here I'm saying assume this phi to be just behaving with respect to some scale a to the power gamma, and then what would happen? So that is the phenomenological way of trying to understand. So now the gauge field equation will look like this. If you write down this equation in this background, and the gauge field potential will look like this. And this behaves like this particular term behaves like a time-dependent mass term. Okay. Notice that if I put this I equal to constant, and which is my conventional electromagnetism, then immediately all the information of the background goes away. And that is what the famous the conformal symmetry of the gauge field. So there are two things. One is conformal symmetry of the gauge field, or while transform invariant of the gauge field. And another one is the conformal flat FLRW. So these two things has to be simultaneously together. Okay. So since this is conformally flat, that conformal symmetry property of this gauge field actually vanishes this A. That is what is that. So that is why I need to, if you want to produce gauge field during inflation in a conformally flat background, you have to introduce some kind of scalar field, some new scale degrees of freedom into the system, such that that non-trivial dynamics of that field will give you the generation of the magnetic. Okay, so then after that you do the standard procedure. You just solve your gauge field equations once you know the dynamics of this new coupling function. And then, and typically I will be using this in our subsequent slides. So basically any gauge field in the asymptotic limit, you can always express in these two. One is ingoing, another is outgoing. If I assume, if I set this coefficient by putting a standard Barnes-Davis vacuum, okay, that would be my, let's say, outgoing, coming towards us, the wave. Then, if I is equal to constant, it will automatically be 0. So that is why we say that in conformally flat background, if I take a minimal gauge field, there is no gauge field production, because this becomes 0. So since there is no time dependent mass term, so there is no production of outgoing mode to ingoing mode. Yeah, so that is what I'll be talking about later. So this is my goal of this paper actually. Okay, so in this conformally flat background, this is 0 if I take I equal to constant. So forget about the usual minimal gauge field configuration. So what I'll be talking about with this I1 non-trivial, meaning this A to the power lambda. So if I do that, I would expect that my production, whatever amount of the production should be proportional to this beta square. Okay. It is similar like Bogoliubov methodology by which you talk about the particle production in the context of time-dependent background. Yes. Yes. Go to the previous slide. This one?
So
yes.
Not only for I equal to constant,
yes,
but even if I is linear in time, with whatever that dot represents.
This one.
In the third equation, the A double dot equation.
Yes.
If I is linear
that
in
is also-
time,
yeah,
that
yeah.
also the mass term goes to 0. And of course, you won't produce any,
Yes,
any
yes,
photons.
yes, that is also true.
However, the coupling there is that linear in time times f square. Do you still call that as a conformal coupling or not?
This one?
Yeah.
Let me see. So if I say A is linear in time, so that means I is linear in time, and then it increases. Okay. Yeah, I think maybe you can.
No, I
Yeah,
think
that's a good
I think
question.
I know. No, I think even if I1 is linear in time, perhaps you can integrate that term by parts. Okay.
That can,
and you will still get a canonical Maxwell term plus a boundary term that you
So
can,
you are saying that
you can throw away.
if it is linear in time,
You can integrate by
absorb it
parts.
somewhere.
You can integrate by parts. You will still get the canonical Maxwell term
that is
and a
possible.
boundary term that you can throw away.
Okay,
So still it will fall within the conformal.
Okay, that is possible. I have not checked this. Yeah, thanks for this pointing out. Okay, so so now I can. Now the methodology is standard. So what you do, you define your, because you assume that your magnetic field is isotropic in nature. So you calculate, to calculate the 2-point correlation function, which can be parameterized by 2 parts. One is this parity even, parity odd. So these are the standard thing that you can calculate. So these are all there in these references. So and then you can calculate what is the spectrum, magnetic spectrum and electric spectrum from this expression with a given behavior of this coupling function, which is a power law that you can clearly see. Okay, what are the takeaways? Once we calculate everything, see that within this range of this gamma, I can certainly produce this magnetic field of order 1 required strength, depending on what is the parameter. You can change your parameter. But the problem is, if you look at that, if you take a particular value of gamma, the scale, the index is different for NB and index higher typically for NB, electric spectrum. So that is why whatever value you take, most of the time what happens, this k to the power I is highly blue tilted. And that blue tilt makes your energy density of this electromagnetic field sometime and most of the time take over and overshoot the background energy density. So that is why you have to do extreme fine tuning. And then you have to take the energy scale of inflation is extremely small. So those are it's complicated. You have to do some cook up. It is not like a very natural thing that to do. And then all the other parameters that is there you can think of are some way or the other they have a problem. If you take gamma greater than 2, it's divergent. You will see that PB becomes divergent. And this is a little bit a theoretical problem. If you take gamma less than 0, what happens? That something called strong coupling problem arises. What does it mean? It means that the way we have started with my gauge field, it is a non-canonical gauge field. So now, if you make it a canonical gauge field, then what would happen? The effective coupling of the gauge field with the fermion or whatever charged particle will enhance by this factor. And now if I is decreasing, because of this I is decreasing, the effective electric charge or effective coupling between gauge field and the electron will be, charged particle will be extremely high. So that means your dynamics of the gauge field that we are talking about is not reliable here, because now it is strongly coupled system. It is whatever we have done is not that reliable. So that is why there is a problem. Okay, so this is a simple takeaway for this particular model. So now, in order to, but taking forward this particular point, people have then talked about a different kind of model where this kind of strong coupling problem is not there. Because now what I do, instead of changing the gauge kinetic function here, I take FF dual, which is pretty much the same kind of operator that you cannot avoid. Of course, it introduces a parity violation in the system, but still you can put this into the system, and then again you put another coupling function. But what is the basic message? By using this, you can also do the same procedure. You follow the same procedure, but finally, what would happen? It turns out that, of course, again, you can produce the magnetic field, sufficient strength, large scale magnetic field, but it produces a large non-Gaussianity. So what is the basic message that I'm talking about is that you can produce large scale magnetic field all the time if you cook up this kind of model, but it is very difficult to get the sufficient strength that we are talking about if you do the model building during the inflation. So that is what I'm trying to tell you. Of course, as I said, you can construct more complicated model introducing more parameters to control your parameters, take your parameter. We have also written, I think Rajiv is also one of my good friends. He does a lot of work on this topic. Okay, so actually this kind of topic that we have recently started anyway. So what is the goal now? This was the goal. What we found is not difficult, but very difficult is to obtain this one if we do everything during inflation. So what I'm trying to do now, rather than amplifying, so basically what we are producing magnetic field at all scale, but we want to get a significant amplification of the magnetic field such that it is of the order of 10 to the minus 17 and 1 megaparsec. But what I'm trying to say is that rather than amplifying during inflation, we can do this enhancement after inflation. Then those sort of problem will not be there. Okay, so that is what we are trying to do. So what I'm doing now, I'm saying let us produce this magnetic field at all scales during inflation, because that is the only way that you can produce magnetic field at all scale. But then I do some modeling at the late time where those kind of problem will not be there, but within the simplistic scenario, where we don't have to do a lot of we don't have to introduce some new models, new parameters and all that. So that is what my goal is. So in that respect, that is what Koushik was mentioning, that inhomogeneity will be playing a very important role in my discussion.
Sorry, so the late time simply also means that, very high redshift, right?
Yes.
In the sense that CMB kind of redshift, or?
Yeah, yes, in some sense, yes.
Because, I don't work on this area, but, many of these popular JWST papers, they actually talk about, quasars and radio galaxies having magnetic field of,
Yes.
something like micro Ghosh at kind of a shift of 10 or 20 kind of thing.
Yes.
So you are not going to worry about those. You want to get like 10 raised to kind of 18 or something like that, which
so
can be amplified by other processes.
Yeah, so depending on the subsequent enhancement mechanism, we can produce magnetic field at various scales.
Okay, sure.
So that is what I'm going to show you.
Okay, thanks.
Time khatam ho gaya. Okay. Okay. So what I'm doing now is that even though your gauge field is conformally invariant, but as I told you that background should be conformally flat, then only gauge field will not be produced. But here we know during inflation we already have background perturbation exists. So this perturbation will be always there. So that means moment there is an inflationary scenario, you always have large scale magnetic field, whatever field it is. You always have non-zero large scale magnetic field at all scales. That is what the first point that I would like to mention. Now if follow the same procedure that we have done, okay? Calculate this, same thing that you do, and then finally you get the energy density of this magnetic field, which is proportional to that beta square that we have discussed earlier. And it turns out that energy density of the magnetic field, because it is just the beta square, it is like a 2-point correlation function that you would expect this should be directly related to the power spectrum, the scalar power spectrum, right? Or curvature power spectrum. And that is what is happening. So my energy density of the magnetic field that is produced from this perturbation will be directly proportional to the curvature power spectrum that we have already. So you can think of a usual power spectrum that we have. Okay, so if you put that value, whatever power spectrum, just standard single roll inflation, standard inflation, where power spectrum we know precisely what is the value, then it automatically tells you that the magnetic field strength should be of the order 10 to minus 46. But remember what I said, that it produces at all scales. That is the main point. And the spectral tilt is very different compared to whatever we have discussed before. So it's a very signature behavior is 3/2. Typically, if you're talking noise, then it is k square, but here it is and k2. So the spectral tilt is very important. We'll see how that is actually going to play a role when you talk about gravitational wave. Okay, so now saying, okay, it is very small. At the inflationary level, can you enhance a bit? Okay, then because people are talking about PBH, why not PBH spectrum? So if I take PBH spectrum, I just take 2 sample PBH spectrum, then let's see what is happening. Okay, if you take what happens, that around the tilt there is a signature of change of magnetic field strength, and here it is like something like inverse cascade is happening. What is happening? The low scale enhancement of the power spectrum of scalar field is giving you a large scale enhancement in the magnetic field. It's like inverse cascade. It's not exactly the same, but it's something similar. Because if you change the peak value of this PBH power spectrum in the higher frequency, it gives you higher and higher magnetic field in lower frequencies, meaning larger wavelength. So my PBH, yes. Yeah, I said 10 to the power minus 23. Yes, that is what I said. Yeah, minus 46. Yes. Yeah, everything is today. Whatever I'm quoting this value, everything is today. I have measured everything at today. Okay, so our simple calculation shows that maximum value of this magnetic field you can enhance depending on what is the maximum frequency that you can think of which exits the horizon. So it is depending on peak frequency, meaning the frequency where the magnetic spectrum, curvature power spectrum is peaked, and then you have this. Okay, and also important to note that there is a peculiar feature. Okay, peculiar feature around that spectrum. So it is like inverse cascade, but of course I would not say inverse cascade here, but it is something similar is happening. Okay, and I can see here, of course, we have not done a very precise model building of inflationary PBH power spectrum, but if I take this typical value of the known and value of the PBH peak value and what should be the height of the peak, then we found that the magnetic value, magnetic strength can be reduced, can be enhanced by of the order of 6 by simply taking the PBH spectrum. Okay, I can enhance, but of course it is not sufficient. That is, it can be of the order of 10 to a 39 or 37 or around 40. Okay, so what is the observation so far? Inflationary perturbation generates magnetic field from quantum vacuum, that is what for sure. Without explicit breaking of conformal invariance, we can certainly generate magnetic fields at all scales. And if you assume the PBH kind of power spectrum, that you can generate of the order 10 to the minus 39 Gauss. So that is what the observation so far. And of course, another thing that I should mention, that we get a distinct behavior of this magnetic power spectrum, which may give you some kind of feature if you look at in the gravitational wave. But remember, I have not done any model building here. Everything except, of course, PBH. Okay. Okay, so now the point is, can we enhance the B field at late time? Because now the question is whether I can produce the magnetic field of that order, what we wanted, 10 to the minus 30, 16 to 17, by using some late time theory. Okay, answer is yes, we can do. We have this famous action photon coupling. You can use QCD, but QCD also has some limitation. But otherwise, if you take any ultralight action coupled with the photon, that can give rise to enhancement. Okay, so let's see. So what is happening? That my action, so one of the assumptions that I made here is action is assumed as spectated throughout, and it starts to oscillate only late time. Late time means after the inflation end, then any time after the reheating, or any time after the end of inflation, depending on what are the parameters that we have. Okay. So these are the parameters of the action. That is the standard equation. So this is nothing new. We have already seen this before. So now inflator will start to oscillate at some scale set by the mass of the action, and you can analytically somehow compute what the oscillation should be. And then if you look at this, then there will be oscillation of this action when it starts a constant, and then moment the mass of the action is of the order of Hubble scale, then it starts to oscillate, because it is similar like any standard scalar field. So moment this starts to oscillate, what would happen? This gauge field will resonantly produce, not resonance here, tachyonic resonance will happen. Because this is also well known. I mean, everything is well known physics here. I'm not doing anything new. So everything is well known. So this tachyonic resonance now can give rise to, now because now you have this parameters, mass and the action decay constant. So there are two parameters here, only two parameters. So you have mass and action decay constant. Now suitably choosing these two values, you can always produce the magnetic field of required strength at any energy scale you want. Okay, so that is what I have shown in this picture. So if I want a required strength around the scale of the order of 10 to the minus 17 and 25, then we found that mass of this action should be of the order of 10 to the minus, very light action, 10 to the minus 20, 10 to the minus 25 GeV. And alpha, the coupling, which is this the action coupled gauge field parameter, should be about 25 to 240. Okay, I'll take just 2-3 minutes to complete. Okay, so this is what we have found, but of course, with the caveat that if I take into account this full back reaction of the gauge field, produced gauge field, and MHD, we have not taken into account that, we will be anyway doing this. Then of course this parameter will change, but I think it is possible to generate magnetic field of that strength, even though we take into account MHD and back reaction. That is what we are our case. Okay, so now this gravitational wave signature. Okay, so moment you have this peak, because what we are doing, we are producing resonantly the gauge field. So that means now this gauge field will lead to a secondary gravitational wave. Okay, naturally you would expect. So that means around this peak value, we would always expect a secondary gravitational wave, and we found that distinct signature of similar like PBH spectrum. If you remember, this is my PBH. And there's a two peak appear. If you remember, we had a talk on this. So exactly in the similar fashion, in the gauge field, because of the gauge field, produced gauge field, there will be a spectrum. There is a GW spectrum, which is like this, is distinct spectrum. And depending on the mass, if you take a QCD action, then for the QCD action, mass is pretty much like a constant from the micro electron volt. 10 to 100 or 1 to, let's say, 10 to 200, 1000 micro electron volt. So within this range, what happens that peak and this distinct signature appears around this Lisa and band. So that means, so that means near future we can always, depending on the value coupling parameter, we can generate along with the sufficient strength of magnetic field. You can generate a gravitational wave spectrum, which is the double peak near around the background PBH GW. Okay, so now if you change the mass, then what would happen? The peak value will be shifting in this side. You can always increase the strength of this peak by changing your alpha parameter. And then the final slide that I would say is, sorry, I'm always going down. Okay, final slide is, what about this particular feature that you have observed in the GW, in the magnetic spectrum due to the scalar power spectrum? So if, of course, this is a bit of fine tuning we require. So if we choose the action mass in such a way that the resonance happens around this point, then your B gauge field production will have this distinct. So if this does not happen around this point, then gauge field production, resonant production will be like this. If this happens around this point, because of this peak, significant change, there is an additional enhancement, because it is, if you go in this direction, there is an enhancement here, and that is why precisely there is enhancement here, and that is imprinted, translated into the gravitational waves like this. Okay, so we have found several interesting features due to so that means here also we found a PBH. So apart from usual PBH spectrum, GW spectrum, we also found analogous signature in the magnetic gravitational wave coming from the magnetic spectrum, and which is encoded here. Okay, with this, I should let me end, and conclusion is for you. I think I'm already late. Okay, thank you very much for your patience. Yeah.
Okay. Thanks, Debaprasad. Questions?
Yes.
There must be a mic there, right? So you go ahead.
I've
and
asked
then
too many
yeah.
questions.
Okay.
Yeah, Alberto. Okay. Go ahead.
That was very interesting. Yeah, thanks. So I have a question about the magnetic field that you're generating, right? Because you are commenting on the no, sorry, yeah, exactly.
Yes.
You're commenting on the values for the axial mass that you require, right?
Yes.
But of course, the magnetic fields you're generating here, they are expected to be fully helical, right? And therefore you
Yes, of course. Yes.
and I mean, and therefore, when you take into account MHD, that's gonna have a very efficient inverse
Further
cascading,
enhancement,
right?
you were saying. Yeah, so that is why then I have to reduce probably alpha 40 to down so that I can produce. I mean, for sufficiently low alpha, I can produce a rather strong magnetic field.
Exactly. So then,
Yes,
that constraint kind of
that part we
will
have not
change
explored.
anything.
Yes,
Yeah.
yes, of course, yes. Yeah, I have not gone into that, but yes.
So here you talked about scalar perturbations. What about tensor perturbations?
Yeah, tensor perturbation is this one. Oh, okay.
I mean,
I understand what you are saying. I understand. Yes, so I think I have. Yeah, we are actually doing that. I have not taken this, but we are doing that. Yes. But you are saying because of the HIJ, what would be the magnetogenesis?
Yeah.
Yes, we are doing that actually. Yes.
Okay.
You have done probably. No?
It's in progress.
Okay.
Yes, okay.
Yeah, I know. Okay. Yes.
Yes, sorry, I have missed some part of your talk. So if you have told, my question will is regarding that. So one of the things people have shown, but so if you produce magnetic field from phase transitions, not from inflation, is the fact that if there is a presence of, like, you produce the magnetic fields and then the phase transition gives you some stochastic gravitational background.
Yes.
That stochastic gravitational background will have a significant anisotropic component because of the presence of magnetic fields. So
yes.
I was just wondering, in this case, when you generate from inflationary magnetogenesis and you look at the gravitational wave, have you looked at the anisotropic part in particular?
In the gravitational wave spectrum.
In the gravitational wave, because I feel that can also be
important signature, that is.
Yeah, particularly the anisotropy and the amount of anisotropy that Lisa, because there are very specific templates of anisotropy that Lisa, I mean the amount which
we have not
Lisa
looked at, no, we
or,
have not gone that far yet, yes. Yes.
When you have a magnetogenesis in a phase transition, there is a problem about the
scales as well as, yes.
So now that you have generated magnetic field at all scales,
yes,
and you are only amplifying at the late universe,
yes,
is there a problem with the coherence length, that the same horizon
yes,
limitation of the coherence length?
No, but that is why, because since we are generating a late time, depending on my parameter, I can produce a magnetic field of this 1 megaparsec as well.
Yeah, but the amplification is limited in a horizon. That doesn't change the fact that you...
No, because I am producing when my universe horizon size of the order 1 megaparsec scale already. So that is why I can produce that 1 megaparsec scale. That is, everything is a causal process now. But since my horizon size is of the order 1 megaparsec, then I can certainly produce this, depending on, of course, what is your mass parameter. You can look at this mass is sufficiently small to generate that. Because you take mass very small, that means you are generating much later.
So basically, if you take this scales, you can probably generate at this 1 megaparsec scale starting from there, right?
Yes.
You don't then need to have an inflation and...
Yes, that is what I'm saying, that you can always produce large scale magnetic field by utilizing this action photon coupling. Yes.
I was just curious to know what is this phi field doing in the end?
Which phi field?
This phi that you have, this axion. I mean, today.
Your ultralight.
Yeah, okay, so two things you can think of. One is, so that is why I said in the beginning that I started with two motivations. One is how to generate magnetic field at all scales, forget about its strength. And then the second problem is how to make it of the order of 10 to the minus 7. So these are the two problems I started with. So by using this inflationary perturbation, I can certainly produce this. And then you can think of this as two things. One, if you assume this action to be QCD action, let's say, then by using this QCD action, we cannot generate magnetic field of this 1 megaparsec scale of this sufficient strength, because QCD action mass is very limited. It is of the order of probably micro. It is of the order of microelectron volt. So if my mass is of the order of microelectron, I cannot generate magnetic field of that strength at 1 megaparsec. So QCD action in some way is not helping us to generate that value. But if I'm not in QCD range but in AL ultralight, then of course we can talk about this. That is point number one. And point number two is we were discussing on the other day somehow that if I take the back reaction, then it is possible that I make my oscillation of the action later by taking into account back reaction. Then there is a possibility that even though within the larger mass of the action, we can generate magnetic field at higher scale. So that we have not taken into account. We have not taken into the back reaction, but back reaction may help in some way. Yes.
All right.
Yes.
Very quick, please. Okay, we are running short on time.
Yes, yes.
Yeah. So I was asking whether you have thought about this implication in the cosmic birefringence in this sense, since you have an axion and the alpha value is moderately large.
Yes, we have not thought about in the sense that yes, actually my PhD work is related to this birefringence, by the way. So we have thought about it, but I have not done this. Yes. Yeah.
All right. So let's thank Debaprasad once again and move on.
Thank you. Thank you.
The next speaker.